camera. Share camera. For whatever reason, I am not there. I can see myself a little bit better now. All right. Where we ended up on Monday was we finished up the section on descriptive statistics, right? And we are now shifting over to a new portion of the class. And this portion of the class is called probability, right? And in probability, we know the rules of nature, or we know the distribution of how things work, right? But what we don't know is exactly how luck is going to play into going forward, into how things are pulled together. For instance, okay, we know how a penny works in terms of flipping a coin. We know, because we intuitively know the physics of looking at it, that if we flip it up into the air, there is a 50% chance it's going to be a 50% chance that it's going to be a head, right? And it's going to be a 50% chance that it is a tail, right? Okay, and all right, let me just verify, because normally the little thing here that says that my that it's recording isn't there, so I have to figure out why it is that it is not showing what it normally shows. Okay, this has me a little bit concerned. Okay, share camera. In fact, I don't even see the little thing here. Let me step backwards. Can you guys see me and hear me? I just want to verify that.
Yes, sir.
All right. You guys, a note that said that it was recording, did you? Because I don't see it on my screen.
On my screen it says recording is in progress.
It does say recording is in progress?
Yes,
okay.
sir.
Okay, super. I have no idea why Blackboard has decided today that that was not something it wanted to share with me. Okay, all right, so be it. All right, so anyways, we are in a world where we know the physics of flipping a coin. We know what the probability is of getting a head or getting a tail. Even though we don't know that, or we do know that, what we don't know is if I'm going to flip a coin in front to start the Super Bowl game, I don't know whether it's going to be the NFC team or the AFC team that shows up on top. I don't know going forward whether it's going to be a head or a tail. But I do know there's a 50-50 chance of either of them happening, right? So when we know the laws of how nature works, but we don't necessarily know what's going to happen into the future, that is called probability, right? And, you know, if you are designing games in Vegas, you have a career in probabilities, right? Okay. When we are trying to figure out what is likely going to happen in the Stanley Cup playoffs, I guess those are the next major sports that are coming up, and the hockey leagues. Okay, we don't know who's going to win, even though we may know who the best team is, right? But the best team doesn't always win. The best team wins more frequently, right? But there's a lot of stuff that goes in, and a lot of that stuff has to do with basically dumb luck, right? And we don't know, how the chips are going to fall, how the coins are going to go, right? And that is the idea of probability. Okay, the thing that ties a little bit these two together, the section on probability and the section we just did on descriptive statistics, is the histogram, right? If I wanted to understand the distribution of, or understand maybe the makeup of a class, okay, I think I had a chart like this, or it was very similar to this on the board on Monday, right? This is a histogram that shows these are the grades, the reading levels of the members of the class, okay? And if I wanted to describe the class's reading ability, okay, to describe that population to folks, one of the things I could possibly do, in addition to giving the mean, the median, the mode, and so on and so forth, is draw a histogram and say, well, how many students were reading at the first grade reading level? 1, right? How many were reading at the second grade reading level? Okay, this is where I found my mistake. Oh, there's 1, right? There was no mistake. How many were reading at the third grade reading level? This student, that student, that student, that student, and that student. There were 5 of them. How many are reading at the fourth grade reading level? 3 of them. 3 of the students, right? How many students are on the 5th grade reading level? Okay, and this is where I had my mistake. And there are 2 students that are on the 6th grade reading level, right? There are a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, there are 13 students in this class. Each one of them has a name. Okay. Now, in my case, I'm not going to call them a name. I'm going to call them student 1, student 2, student 3, student I, right? All the way to the N, the last student, which is the 13th, capital N equals 13, right? And I can give you a visual look of what that class looks like by creating a histogram. Right? Now, there are 13 students total on my list. And when you add up this histogram, you would end up with 13. Okay? Now, I am going to ask the question, what is the odds if I put every student's name into a hat, mix them up really good, and pull a name out at random? What is the probability that I get someone who is reading at the first grade reading level? Well, how many students fit that characteristic? 1 student, right, from here. How many are there total? There's 13 students total, right? So the probability is 1/13. And I am going to draw a chart in blue over here. I can go right. Probability of getting a student that is reading at the first grade reading level is this. What is the probability of getting a student that reads at the second grade reading level? Well, student number 2, Mary, reads at the second reading level. the odds of getting that are 1 out of 13. Right? What are the odds of getting somebody who is reading at the 3rd grade reading level? Well, by reaching to the bowl, I could get this student, I could get this student, I could get this student, 1, 2, 3. I could get this student, and I could get this student. There are a total of 5, right? The probability that I get a student that reads at the 3rd grade reading level is 5/13. Right? What about the probability that I get someone who reads at the 4th grade reading level? I could get this student, I could get student number 12, I could get student number 11, and I could get student number 1, right? 3 out of the 13, okay, read at that level. So the probability that I get one of those 3 is 3/13. How about 5th grade reading level? Again, there is only 1 out of the 13. Okay, so my odds of getting it are that. Okay, and then when we look at the 6th grade reading level, we end up with 2 out of the 13. Okay. Now, just looking at the shape of what we had here in that histogram, which described the population of students in terms of their reading level, right? And this, which is the probability of picking someone with these various characteristics. What can you tell me about the shape of the 2 histograms? They have the same shape, right? The heights are different because instead of being a height of 5, over here it's a height of 5 divided by 13, 5/13, right? Okay. So my whole scale over here is different than the scale over on this side, but the shape of the curve is the same. Okay. We will call what I just drew over here a probability distribution. If I know this to be a fact, which is the distribution of the population, if I know this to be a fact, that this is the number of people in the 1st reading level and the 3rd reading level and so on and so forth, if I know this to be the fact, this over here is the probability distribution that if I take a student, I will get someone that falls into one of these grade levels, reading grade levels, right? When I add all of these together, I'm going to add up. If I add them all together, I get a total of 13, right? If I add up all of these histogram bars, I stack them one on top of the other, what's my sum of all of them? The sum of all of them, adding them all together, is going to equal 1, right? This will tell me, if if I know the probability distribution, I can draw a histogram like this. There are a few rules for a histogram to be a probability distribution. Rule number one, all of these together have to add up to 1.0. Okay. The probability that I get one of these is 1. I will either get a first grader or a second grade reading level, a third grade reading level, fourth grade reading, fifth grade, sixth grade, right? The probability that what I pick is in at least one of these bars is 100% because we didn't have anybody that read outside of those reading levels. Okay? So, rule number one for a probability distribution is the sum of all of the bars has to equal 1.0. Or sometimes we will express these not as a fraction, sometimes we'll do them as a decimal, and sometimes we will do them as a percent. Well, what percent equals 1.0? Percent is per 100, right? So 100% is the same thing as 1.0, right? So for a distribution, or a histogram to be a probability distribution, okay, if I sum them all together, they have to equal 1 or 100%. That's rule number one. Rule number two. Okay, is that all bars are greater than 0 or equal to 0. There can be no negative bars. The probability that I get someone who reads at a certain, let's say the 7th grade reading level, is 0 in this case. There is no bar, right? But I cannot say, and it makes no sense to say, the probability is negative. 0 is as low as you can go. Something that's impossible happens with a probability of 0. It does not happen with a negative probability, right? So, rule number two is all bars have to equal, be greater than or 0, or that another way to phrase that is none are negative. The third item out of 4, okay, is that every possibility that could happen is at least in one bar. So somebody could be at the 3rd grade reading level, they could be at the 4th grade reading level, but everyone that is in that class is in one bar. Okay? We didn't skip a bar. Okay? Which is good news, because to some degree, if we had skipped a bar that had people in it would be a 0, right? And all of them wouldn't add up to 1 if we had indeed left out 1, right? So every possibility is in 1 bar. And then our last one rule number 4, okay, is in 1 bar. No event is in more than 1 bar. For a graph, for a histogram to be a probability distribution, they have to satisfy 4 rules. Rule number 1, they have to add up to 1 or 100%. Rule 2, all bars have to be positive. There could be some zeros in here, but there cannot be any negatives. Right? Rule 3, every possibility has to have a column which describes it. So this person has to have a column, and indeed the person here and the person here, these 2 people are represented in the bar 6. This person is represented. This person is represented in that bar. Every single possibility is represented in 1 bar somewhere. Okay? The last one is each of these are represented in 1 and only 1 bar. We do not have someone who could be reading at the 2nd grade and the 5th grade reading level simultaneously. They are counted either as being a 2nd grade reader or a 5th grade reader. Okay? And if we satisfy these 4 rules, we will say that we are looking at a probability distribution. Okay? So the most important of these, they're all equally important. Okay? But if we see something like this, it is a probability distribution. If we see something that violates this, we do not have a legal probability distribution. Okay? So let me show you a probability distribution that looks a little weird and is a little different than this, and I'm not sure why we would do this, but here is another probability distribution. Okay. Even. What I just drew here, is this a probability distribution? Well, what am I representing here? I've got a histogram bar for 1st grade reading level, for third grade reading level, for fifth grade reading level, or if the reading level of that student is an even number. What are the even numbers? Obviously, 2, 4, or 6. Let's ask the question, is this a probability distribution? No. It may not be one that makes an awful lot of sense, right? But if you're playing roulette, maybe something like this does make sense. I don't know. Okay, but is it a legal probability distribution? Well, they add up to 1. 1/13 plus 5/13 is what? 6/13 plus 1 is 1/13 is 7/13 plus 6/13 is 13/13. What is 13/13? 13 divided by 13 is 1, or 100%. Bingo. This satisfies rule 1. Does it satisfy rule 2? In rule 2, all bars are greater than 0. Do we have any bars here that are negative? No. We don't have any bars that we have 0 being down here. We don't have any bars that go negative. Rule 2 satisfied. Rule 3, every possibility is in one bar, is in one bar. Is 4 in one bar, this first student? Yeah. Fits into that category. Is this student in one of the bars? Yeah, again, student 2 is counted in the even category. Is 1? Yeah, we have a bar for 1. Do we have a bar where the 3s are counted? Yes. Do we have a bar where the 5 is counted? Yes. Do we have a bar where this 3 is counted again? Yes. Do we have a bar where the 6 is counted? Yes, it's an even number. Do we have a bar where this 3 is counted? Yes. Bar where this 3 is counted? Yes. Do we have a bar where this 4 is counted? Yes. Do we have a bar where this is counted, this 4? Yes. And how about that 6? Yes. It satisfies rule 3. Every possibility that might be possible is in one of these bars. Rule number 4. Is there any event that is in more than one bar? Well, I went through each one of these, and at no point did I ever say, yeah, there are 2 possibilities for this, right? No. Of these 4 bars, there's only one spot where this 4th grade reader fits in, which is the even one. There's only one spot here, and so on and so forth. When I went through that list, at no time did I say, oh, yeah, there are 2 spots where that person is counted, right? Where that student is counted. So we satisfy rule number 4. No event, no student is in more than one bar. And hence, this is a legal probability distribution. And we deal with it as a histogram. Right? Now, if I wanted to ask the question, what is the probability of an event happening that is one of these bars? I can read it right off of the bar. If I wanted to ask the question, what is the probability of one of these things? What is the probability that I am in one or more than those bars? I would add up the probability in the total sum. right? So what is the probability that the reading level of a student that I take at random is an odd number? Okay. Well, an odd number would happen here, here, here. An odd number would not happen in the category that is even, right? So what is the probability of us getting an odd number? It is the probability of this plus the probability of getting that plus the probability of getting this. So the odds of us getting an odd number in terms of the reading level when we take a student out of the hat would be 1/13 plus 5/13 plus 1/13, 1, 6, 7. So the probability of getting an odd number is 7/13. Okay, so we can figure things out from looking at the probability function if the probability thing allows us to do that. Okay, so we could also do, well, something we can't do is what is the probability that it is a prime number? Well, I've got a little bit of a problem here, okay, because I can't do it from here. One is I would have to go back to my math book. I don't actually know, is 1 a prime number or not, right? Okay. I know 2 is a prime number, but this version of this probability function doesn't break out the evens to the 2s, the 4s, and the 6s. And I know 4 is not a prime number and 6 isn't a prime number. So I can't do that. I know 3 is a prime number, would be included, this would be included, but I don't have the information on this probability function to be able to answer that, right? Because it's not a fair adding of columns together. Now, had I described the probability function in this one over here, now I could possibly do it. I would say a prime number. I'm assuming for the moment that 1 is not a prime number, although it probably is. Does anybody remember from their math whether 1 is a prime number or not? No? Okay, so you're all on the same boat I am. So 2 is a prime number, 3 is a prime number, 4 is not, 5 is a prime number, 6 is not. Let us assume that 1 is. The more I'm thinking about it, the more 1 is probably a prime number. I can say, what is the probability that I pick out a reading level that is a prime number? It's 1/13 plus 1/13 plus 5/13 plus 1/13. What is the probability I get someone who is not a prime number? Well, that would be the 4, the bar for the 4, and the bar for the 6. Okay. You guys sort of get this feeling of how to function and read probability distributions. The rules are relatively straightforward. They make sense, right? Any other comments about this? All right. We are going to, in this section, there are 2 categories of variables, and we will call these variables, we call them random variables because there is a randomness that we will get different results. But there are 2 different types of charts like this. The one that I just did is called a discrete probability distribution. The word discrete means we have discrete little bars. Okay? By the way, these bars here had to do with reading levels, right? I could have a bar that is girls, boys, right, in the class. I could have brunettes, blondes, redheads, and people with no hair. I don't know if I'm missing something, right, in terms of distribution, right? These buckets, these bars, could be characteristics that are not something that is a number. Well, the labels wouldn't be numbers. How many you have and what the probability of you getting that, so those would be numbers, right? Below, it would be 0. Oh, by the way, none of these can be, they can't be, I didn't write it, but none of these numbers can be less than 0, right? That I wrote down. But a thing that I didn't write down, but it's a corollary to it, no number could be greater than 1. Okay? The probability of any specific action happening cannot be more than 100%. Well, if any of these bars were over 100%, and when you add up all of the sizes of the bars, you have to end up with 100%, means you must be adding something that is a negative number, which we said can't happen, right? So I said one of the rules that I did not write down, because I don't have to, because it would be that none of these heights of these histograms on a probability distribution can be greater than 1. But if anyone were to be greater than 1, we would know we would have a violation somewhere else, because when we add them together, if one individual one is over 1, that means we had to subtract something to get there, and since none of these bars can be negative, I don't need that as a rule, right? It sort of falls into as a rule that will always be, but it doesn't have to be a written rule. All right? But down on the bottom, we could have male, female. We could have things that look like numbers, but don't really, that really aren't anything other than a label, like the UPC code on cereal boxes, right? I could have how many different people buy different cereal boxes, and each one of these down on the bottom, each bar could be, you know, Captain Crunch and Post Oats and More and Rice Krispies and things like that. The UPC symbol on the bottom of it, you know, maybe a number, but it doesn't mean anything. It's just a label. Just like my zip code is a label. Okay, I'm not sure that my zip code and your zip code give an awful lot of information. Okay, certainly not numbers. Okay? Not in that sense. All right. All right. So we have that. When we have bars like this, we call that a discrete probability distribution. Now, the alternative to discrete is continuous. In continuous, I'm going to leave those up there for a few seconds. We can use an example such as you going to the gas station to fill up the tank of your car. And if people's cars have a 20-gallon tank, right? And I watch however people fill up. Some people who fill up at the gas station put like a gallon in. Some people put in a little less than a gallon, like 8/10 of a gallon. When I've got to rent a car and I have to return it full, I will typically go to the gas station right in front of the airport where I have to drop off the car, and I will fill up the tank, and it usually is less than a gallon, right? Why? Because I usually have filled it up like 30 miles earlier when I went past a cheap gas station, right? Okay, because I figured right at the airport, they kind of got you over a barrel. The prices are probably high right near the airport, so I'm gonna fill up when I go past Sam's Club, right? And then I'll just top it off, right? So sometimes you have people who fill up the tank with less than 1 gallon. Sometimes you have to see people fill up the gas with a little bit more than 1 gallon, like 1.2 gallons, or 1.287 gallons, or 1.28763 gallons. You could be filling up your gas tank with any number from 0 to 20 gallons, right? And it would be a continuum. You don't have to say, oh, I'm going to fill it with exactly 1 gallon or 2 gallons or 3 gallons or 4 gallons or 5 gallons all the way up to 20. I will end up with a continuous line that it's possible. At which point my probability function may look something like this. Okay. Now, when you see a probability distribution that is a line like this and not a histogram, okay, we will call this a continuous probability distribution, and we will have very, very similar rules. Okay. Rule number 1 was when we add everything together, it has to equal 1, right? The old rule was when we add all the bars together, it has to equal 1. The new version is if we take the area under the curve, this area has to equal 1. Okay? So rule number 1 is the area under curve equals 1.2. Rule number 2. What was our old rule number 2? Was we can have no negative dips. A continuous probability distribution can go down to 0, but it can never go negative. Okay? So something like this, where the line goes negative, can never happen. Okay, so let's, okay. Line can never go negative. It can go to 0, but it can't go negative. Right? Event number 3 is that everything is possible and it is shown somewhere. And this one, in a continuous distribution, is almost always satisfied just because we start with 0 and we go to 20, and any number that is in between there is there. I can show it as being somewhere on this continuum, right? And by the way, if this is 14.673, and this number is 3.872, these will never overlap. Each point here from 0 to 20 is its own decimal place that goes on for infinity, right? And two decimal places, two different numbers, will always be two different points from 0 to 20, so they will never overlap. So 3 gets satisfied and 4 gets satisfied. So if we have a curve where the area underneath that is 1, okay, and that curve never goes negative, number 3 and number 4 are always going to be satisfied pretty much accidentally, right? Okay. We then have a probability function. Okay. It is a continuous probability function, whereas when we did it with bars, right, it was a discrete probability function. All right. With that, I think I'm out of time today. We will continue on with this, and we'll start doing probability trees starting on Friday. Meanwhile, continue on the first chapters that we had worked on, chapters, I think, 1 through 4. I think it was 1 through 4. All the material up until now that was descriptive statistics, and we have a test on that coming up on Monday. All right. Any questions? No questions? You guys still continue to hear me, right? Yes?
Yes, sir.
Good. Okay. All right. Because I still don't see where my button is for the recording, and I don't see the button to turn off the recording. So hopefully here in a second, when I log off, we'll be in good shape.
Are we going to have a review Friday for exam number 1?
I'm sorry, what was the question?
We're going to have a review on Friday for the coming up exam on Monday, sir.
Well, I'll tell you what, if you got any questions, I'm be more than, I wasn't planning on having, quote, a review, but I will absolutely entertain any questions that anybody has. So between now and Friday, if there's anything you come up with that say, you know what, this part of what you described was as clear as mud, right? Can you talk about that in a little bit more detail? I'd be more than happy to spend time on Friday or all time on Friday to answer any questions.
Okay.
Does that make sense?
Yes, sir. Thank you very much.
Yeah. So yeah, just think of whatever it is that you would need a review on, and I guess if you're going to call that a review, the answer is yeah, I'd be up to that. But I'm not going to proactively, if none of you have any questions, bore you in going over material that none of you seem to have problems with.
Okay. Thank you.
All right. And the test itself is probably going to be, I would say, probably 5 or so, maybe 6 short answers. Maybe a little bit of math involved. Make sure you sort of understand the homeworks. I might have something in there on Excel, a little bit on the homework from Excel. How do you compute the various things? How do you compute mean? How do you compute median? How do you figure out how mode is? How do you compute the standard deviation? Right? Now, I'm not going to give you, 4 hours worth of TDO math, but I might say, here's a number of 5 numbers, a population or a sample of 5 numbers, where it's not going to take you 3 hours to calculate, right? Because I'm going to want to see, do you understand the concept of it, right? It's not can you do everything, you're going to end up in real world environments doing most things on the computer anyway, right? So what I need you to do is be able to do it by hand so you can verify that the computer is doing things the way you think that it should, so that you understand the owner's manual of whatever software or whatever calculator you're using. And that becomes even more important now because it looks like about 10 years ago, people stopped giving owner's manuals. Okay? They figured, okay, maybe there's some help functions or something like that. But it used to be that when you got a copy of Excel, you would get an owner's manual that is about that big that would teach you how to use the various functions. Nowadays, you just throw it in and maybe it makes sense, maybe it doesn't make sense, right? And we get into that big problem of, why do I make you do it by hand? A good example is in Excel there is a function, STDEV, standard deviation, right? And then you can put the numbers behind it you want a standard deviation of. Very simple, very usable. But here's my question to you, right? Did it just give you the population standard deviation, or did it give you the sample standard deviation? Now, the answer is, I don't know. Well, it used to be that when you had a manual, it would tell you what it would be, right? But it's not at all clear anymore. So you got to be careful that when you use equipment, when you use software, that what you think it is doing is actually what it is doing. And once you can verify that and feel comfortable that you know how to use the software, then go ahead and use it, right? Okay, but we got that, issue that, I kind of told you my first promotion was because the information that was on the computer systems was not what everybody thought it was, right? The equal standard STDEV function, and by the way, in the meanwhile, Excel has added other functions to add clarity, but they kept on using that old one because people who had used Excel 20 years ago and written it into code are still using it, so they didn't rip something out that was usable, but they now have added more functions that do standard deviation for population and sample. And there's more than one that does exactly the same thing, which adds more confusion in Excel than anything else. All right, any other questions? Okay, if there aren't any other questions, I am going to call it quits, and we will see everybody on Friday. All right? Okay, bye-bye. Now let us see.